Okay, so here's the singularity, which would be the Higgs boson. Now, when you track their decay, they decay backwards, and this would be the most fundamental particle that there is, the electron. But is it? Now, I theorize that neutrinos make up electrons, and the space roar itself, because sound is loud, will stick these neutrinos together to form the electron, making it the only fundamental particle that there is from neutrinos. Basically meaning that you can't break the electron apart because the subsonic space roar of sound, just the void of space, because it is big and empty, the echo of it, literally fundamentally sticks the neutrinos together to make an electron. And there'd be about 232.272727 neutrinos stuck together, because since it doesn't decay into an electron neutrino, the muon does. So since it does, ultimately, this would be the most fundamental particle, and it'd be composed of neutrinos. Now, when you put them together, 232.272727 times 207, because this is 207 times this, and then this is 17 times this, and then the Higgs boson is 74.5 times bigger than this. You get 60,893,895.610319 neutrinos, because basically everything's made of light. Now, everything's not necessarily made of photons, everything's made of neutrinos. Neutrinos are light, too. They're the lightest of the light, hence the term light. Now, once the Higgs boson or the singularity forms, since it is relative to only space, it's in a fifth-dimensional relativity. So it's relative to fifth-dimensional hyperspace because it's the only thing that exists. This means it's in a quantum superposition. That means technically it's huge, because if you zoom in on it, it's got the mass of the whole universe. That means it's huge. But relative to space, it's only a dot. So it's a dot and it's huge at the same time, relatively. Not to mention the fact that technically it has no spin, even though it's spinning. Now, since it's relative to space, hyperdimensional space, it has no spin that can be measured. Because if you were tied to a rope and you were looking at the center, you wouldn't see it spin even if it was. You'd just see the star itself, or the singularity. If you were looking back at interstellar space, or just the void of black space, you would only see blackness even if you were moving. So technically, you wouldn't be moving at all even if you were. Now, this is the problem with scientists. They tend to cut the rope between them and the star, or the singularity, ultimately adding themselves. So now they're in this space relative to the singularity, when technically there was no relativity except for the hyperdimensional space. So what it's going to do is, since this is a three-dimensional physicality, it has a physical three-dimensional form, it's going to drop into a fourth-dimensional state because it's relative in the fifth dimension, and it wants to actually have some kind of time and decay. So it's a three-dimensional physicality in a fifth-dimensional state, and it drops to a fourth dimension, which is time and relativity. So now, since it drops and it loses that energy, now it can actually decay, and time can apply. So while giving this mass, so it traded that spin for mass. And then, of course, it's going to decay into the bottom quark. The bottom quark is going to decay into a charm and an up quark and a down quark. The charm quark itself will decay into a strange, which will decay into an up quark. And of course, while doing this, it emits a W boson. Now, the W positive and negative bosons are a residual measurement, like a gluon. Now, let's say you have a year, because our planet orbits the sun. We have to measure it with a year. Now, because you have these gluons, well, you have quarks moving around, that would be considered the orbit. So you have a gluon as its measurement. So a gluon is an analogy to what is a year on our scale with Earth. It's not a particle, it's just a measurement of something. It's a residual trait. So basically, the static sticks the neutrinos together, which forms the electron, which is a -1 charge. It gains energy, ultimately becoming the singularity, and it'll lose energy to stabilize into up and down quarks. Now, this is basically the scalar field. This is analogous to a sound circuit. This side over here is a temporal field, which is analogous to a light circuit. If you add all of the leptons up, you get 1.8 giga electron volts. If you add up all the quarks, you get 180 giga electron volts, which is 0.60 times 3. And this is 60 times 3. So that's why you would get the circle, the temporal field. And to square the circle would basically be 9, 18, 27, 36. The angels standing at all four corners of the earth, or the angles, 180-degree angle here, 180-degree angle here, which are basically 90-degree angles. Okay, so the singularity basically has its poles, and the more that it compresses, the more spin it's going to get. So it's in fifth-dimensional hyperspace relativity, like I mentioned before, and it's going to drop to the fourth dimension. That means it's going to drop from one spin to a half spin. And the God particle, or Higgs boson, is going to go from 126 giga-electron volts to 179 in the quark, top quark, as it starts to accelerate out, flip. So that three-dimensional vector essentially goes into a three-dimensional vector with a fourth-dimensional field, which is time, around it. Technically, to have any time, you actually need more than one thing relative to empty space. If I only have one thing, it's in fifth dimension. It's in a superposition. But if I have something else relative to it, then I can have a measurement, which is time, because then I can measure decay and or distance. And essentially, the quasar is the last stage, and it mirrors its mother, or you could say its father, its parent model. So this is the singularity, and it is a star, essentially. It's a giant neutron star that forms a nebula. Like if we observe a neutron star long enough, I'm willing to bet that it turns into a galactic nebula. It'll turn into a small universe. It'll be a small universe within a universe. And that'll turn into little galaxies because it has enough energy in it to do something like that. For that kind of enterprise, a neutron star has that kind of energy. So a macroneutron star formed a galactic nebula, which is basically a nebula of galaxies, what we call a universe. So this is the centripetal force giving this spin, and then this is the centrifugal slinging out. And that slinging out is anti-gravity, or dark energy, or literally the weight of the universe recoiling. This is analogous to the one spin of the Higgs boson, essentially. Whenever the gravity pushes down, you see the weight of it. And then whenever it flies out, it's going to drop that spin to a half spin, but it's going to give the top quark a lot of energy. With that being said, when it comes to matter and antimatter, I believe they're actually, matter that we see is actually antimatter and matter combined as composites, because everything's made of neutrinos. So if you have all these neutrinos that are bound together, and because they're neutrals, okay, but if you have more neutrinos in one area than you do more than you have in a different area, then you have more of a positive charge. So let's say you have 100 neutrinos here and 50 neutrinos here. You have a positive and negative charge from neutral light, from light essentially. And they're fractionally, since it's all composite, when you break them apart prematurely, you'll have fragments of what we would consider antimatter. Because now it's not bound together anymore. It's got an opposite charge because technically it was bound together and interwoven with the antimatter. This is why we have CP symmetry and CP breaking. Essentially, everything is made of antimatter and matter. It just depends on its polarity. Right now, we just happen to be in the resonance that we are right now, the vibrating. See, whenever you put matter and antimatter together, they explode. Now, the universe's weight, and since everything happened through the singularity process, it pushed all these neutrinos into essentially electrons and composite vibrations of particles in a small one-dimensional field, essentially. And then a two-dimensional, and then we reach our three-dimensional. But ultimately, on this scale here, on the quantum scale, even smaller than what we would consider quantum, the neutrinos are composite. And that's why you can take a positron and it'll repel a proton, because they're both positively charged, but one's antimatter and one's matter. That indicates that they have to be made of the same thing, and that's basically light. Because if they were made of something completely different, when they hit each other, they wouldn't repel. Even if they both are positively charged, they would actually annihilate also, because they're completely different. So this means that since, even if it's antimatter, it'll still repel when it comes to something that's matter. That means they have to be made of the same thing. And everything is made of light, no matter what the charge is. It just depends on what scale. So essentially, whenever they explode, when you touch them, like if we take some antimatter and we take some antimatter or and some matter and then just put them together, they have opposite charges, boom, they're going to explode. Now, this is what's happening on a very, very small scale with the vibrating and the energy and the color charge. Everything is exploding, but it's exploding to the point where it can't explode and spread out. It's bound in him together. So it's vibrating. It's almost like it's trying to explode and come together and explode and come together at a very, 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 very high frequency. And that's what gives matter the frequency it has. That's matter's frequency. This is the best way to explain it. When it gets to the point where it's vibrating so fast it looks like it's hovering, but it's bouncing, that's on the micro scale explosion that I'm talking about. And that's what makes us able to see whatever matter it is. It's at such a resonance that that little space in between them, that's like analogous to the particles and the empty space inside atoms. Now, technically, all this empty space in here can't be reached because this acts as a force field around the nucleus. The electron does. So it's analogous to this right here spinning. Now, I can't put my hand through there because it's spinning so fast, there's like a force field there. Now, let's say I slow that energy down to the point where it's nearly frozen. Now, I can put my hand through there, and that's what a boson-sun condensate essentially does.